Hello everybody and welcome to the Acids, Bases, pH and Buffers tutorial from the A-Level Cookbook, Recipes to Survive A-Levels. So today we're going to be talking about Brønsted-Lowry acids and bases, the dissociation of acids and bases, their reactions, calculating pH of acids, monoprotic and diprotic acids, the ionic product of water, the pH of bases, the acid dissociation constant Ka and pKa, acidic and basic buffers, and then calculations using buffers. Let's talk about what Brønsted-Lowry acids and bases are. This is just a theory that explains the interactions between acids and bases. So Brønsted-Lowry acids are proton donors. What this means is that they release H plus ions when dissolved in water. Although you might see H plus written in chemical equations, in reality it doesn't exist on its own and it forms hydroxonium ions, which is H3O plus. Throughout the acids and bases topic, it's helpful to represent acids as HA and bases as B. So for example, with the acid HA, if you add water to it, it forms H3O plus and A minus. And if we take this with an actual acid such as hydrochloric acid, you get HCl plus H2O gives you H3O plus and Cl minus. Brønsted-Lowry bases are proton acceptors, and if you dissolve a base in water, they combine with H plus ions from water. So for in this example here, the base B and water gives you BH plus, it's accepted the proton and OH minus. And an example is ammonia. If you combine ammonia with water, you get NH4 plus and OH minus. It has accepted that proton. You can see that there's an H plus on this here, where it wasn't here. So let's talk about the dissociation of acids and bases. Dissociation describes the breaking up of acids and bases into their positively and negatively charged ions. Strong acids and bases dissociate nearly completely in solution. It is important to note that dissociation is actually reversible, but for strong acids and bases, the equilibria is so far to the right, we might as well consider them to just be straight reactions. So we've got HNO3, nitric acid, dissociating into H plus at NO3 minus, and we've got a strong base such as potassium hydroxide, which dissociates into K plus and OH minus. It's also important to note that strength and concentration of acids are not the same. Strength measures how far the dissociation goes, so how far to the right this equilibrium is. Concentration is how dilute an acid is. I could have nitric acid, for example, which is a strong acid, and dilute it a lot. It's not very concentrated, but it's still a strong acid. Although I mentioned before that H plus on its own doesn't exist and it actually forms hydroxonium ions, you don't really need to write this in exams unless water is acting as a base, because the water is taking on that proton. So for example, if you have a question where it's something like, write the equation for the reaction between hydrochloric acid and water, this is where you would have to include the hydroxonium ion. So you can see here HCl plus H2O gives you H3O plus and Cl minus. The acid has dissociated into H plus and OH minus, but the H plus has gone to this water, it has accepted it. And like I mentioned before, Brønsted-Lowry bases accept a proton. The water here is acting as a Brønsted-Lowry base because it has taken on that proton. Let's talk about weak acids and bases. They only slightly dissociate in water. Their equilibria is actually really far to the left, therefore their equilibria plays a more important role, which we'll get to when we talk about Ka. An example is ethanoic acid, which dissociates into ethanoate ions and protons, and an example of a weak base is ammonia, which when added to water forms ammonium ions and OH minus. So let's talk about the reactions between acids and bases. So protons cannot be thrown away without a base. It can only be donated if there's something to accept them. So if we have an acid HA and a base B, this is the reaction that takes place. The H plus from the acid is given to the base here, so it's been accepted by the base. So you've got BH plus, and the acid has donated its proton, so you've got that A minus there. So let's talk about calculating the pH of acids. So hydrogen ion concentration can vary massively. Some have absolutely massive values, others have tiny values. So to combat this problem of having numbers that are just so wide in range, we use a logarithmic scale. So to work out the pH, you type in on your calculator negative log to the base 10 of the H plus concentration, the hydrogen ion concentration. The reason that there's a negative sign is because it just makes the number look nicer. If you put log to the base 10 of like 0.1 in, then the answer's negative. For example, a typical question might be something like, calculate the pH of a solution that has a hydrogen ion concentration of 0.025 moles per decimeter cubed. They've told you the hydrogen ion concentration, which is what you need to work out the pH, so you could stick that in your calculator and you get 1.6. It's also important to appreciate the pH scale goes from 0, which is extremely acidic, to 14, which is very alkaline, and a pH of 7 is considered neutral, and pure water is considered to have a pH of 7. Well, we can use the reverse to work out the hydrogen ion concentration, which is just 10 to the power of the negative value of pH. For example, a solution has a pH of 3.54. Find the hydrogen ion concentration of this solution. All you would do is you just put 10 to the power of minus 3.54, which gives you 2.88 times 10 to the minus 4 moles per decimeter cubed. Do not forget to include the units because you are measuring a concentration here. Let's talk about strong monoprotic acids. So a monoprotic acid is an acid that releases 1 mole of H plus ions for each molecule of acid. So every single acid that dissociates gives away 1 proton. Examples are hydrochloric acid HCl and nitric acid HNO3. So if we take nitric acid, its dissociation equation is that. So you've got HNO3 dissociates into 1 H plus and 1 NO3 minus. And like I said before, throughout this we'll start writing HA and A minus just to make it easier because some acids have quite long formulae, it's just helpful to write HA and A minus. So since dissociation is in a 1-to-1 ratio between the acid and the H+, there's one HNO3 here and then one H+ there, the concentration of H+ is equal to the concentration of HA because you have the same number of moles dissolved in the same solution. This is quite helpful because we can use this to work out questions where they've given us the pH of the acid without telling us the hydrogen ion concentration. So for example, calculate the pH of 0.065 moles per decimeter cubed hydrochloric acid. It's always helpful to write out the equation of its dissociation to put it into perspective. So HCl dissociates into H plus and Cl minus. You can see there's a 1-to-1 ratio between the HCl and the H plus, so the concentration of H plus is the same as the concentration of the acid, which we've been told is 0.065. Now that we know H plus, we can put that into the pH equation and work out the pH. If you do that, you get a pH of 1.19. This method does not work on weak acids, which we'll cover later. The reason being is because weak acids do not nearly fully dissociate, and their equilibria plays more of a role. So let's talk about strong diprotic acids. So diprotic acids, as the name suggests, release 2 moles of H plus ions for each molecule of an acid released. And a key example is H2SO4 or sulfuric acid. If we write the equation of its dissociation out, you get H2SO4 goes to 2H plus and SO4 2 minus. So there is a 1-to-2 ratio now between the H2SO4 and the 2H plus. So since the dissociation is in a 1-to-2 ratio now, the H plus ion concentration is 2 times that of the acid. For example, calculate the pH of 0.095 moles per decimeter cubed sulfuric acid. So write out the equation again. You've got H2SO4 dissociating into 2H plus and SO4 2 minus. You can see here that there's 2 times as many H pluses for every single acid. So the hydrogen ion concentration is going to be 2 times that of the acid, which is 0.095 times 2, and that gives you 0.19 moles per decimeter cubed. Stick that into your calculator and the pH comes out to be 0.72. Again, these methods do not work on weak acids, they only work on strong acids. We'll talk about weak acids when we get to Ka. Let's give you some examples to practice. Just pause the video after I show you the question and I'll show you the solution. So calculate the pH of a 0.3 mole per decimeter cubed solution of HCl. I'll give you a second just to try this question and then just press play after. Okay, I hope you enjoyed doing the question. So as always, write out an equation for the dissociation. So you've got HCl dissociates into H plus and Cl minus. Because they're in a 1-to-1 ratio, the concentration of H plus is going to equal the concentration of the HCl. Therefore, the concentration of H plus is 0.3 moles per decimeter cubed. Stick that into your pH equation and you get a pH of 0.52. Try this example as well. Calculate the pH of a 0.23 mole per decimeter cubed solution of H2SO4. Just press play when you finish the question and I'll show you the solution. Okay, so as always, we write out the equation of the dissociation of this acid. So we've got H2SO4 going to 2H plus and SO4 2 minus. You can see that there's a 2-to-1 ratio of H plus to acid. Therefore, the concentration of H plus is 2 times that of the acid. That gives us 0.46 moles per decimeter cubed. Then you can stick that into the pH equation and you get a pH of 0.33. Let's talk about the ionic product of water. Now this is quite important when working out the pH of strong bases, which is why I've put it here. So Kw is another equilibrium constant. So you've got Kc, you've got Kp, and Ka. Kw is another one. And it's written as Kw equals the concentration of H plus times the concentration of OH minus. Its units are mole squared dm to the minus 6, because you're timesing a concentration, which is measured in moles per decimeter cubed, by another concentration, also with the units moles per decimeter cubed. And when you're timesing things like that, you add the indices. So you have moles to the power of 1 times moles to the power of 1. 1 plus 1 is 2. And you've got dm to the minus 3, dm to the minus 3, minus 3 plus minus 3 is minus 6. As with every other equilibrium constant in existence, the only factor that changes it is temperature, which is why in questions they might say something like the value of Kw at room temperature, 298 kelvins, is 1 times 10 to the minus 14. In pure water, there is 1 H plus for every OH minus, therefore you can assume that H plus's concentration is the same as OH minus. So whenever you have cases of pure water, Kw is equal to H plus squared. They might give you a question where they want you to find the pH of pure water at a temperature that's different to 298 Kelvin. In that case, you can make this assumption. At 298 Kelvin, Kw is 1 times 10 to the minus 14. Talking about calculating the pH of strong bases, this depends on the use of Kw. You use Kw to find H+. So strong bases such as sodium hydroxide and potassium hydroxide nearly fully dissociate in solution. So if we look at sodium hydroxide, it has this formula here, NaOH going to Na plus and OH minus. Since the dissociation is in a 1-to-1 ratio between NaOH and OH minus, the OH minus concentration is the same as the NaOH. But to work out the pH of anything, we need H+, but there's no H+ here. This is where Kw comes in. So whenever you're in a scenario where you have strong bases and you have OH minus but you don't have H+, you need to use Kw because that links them together. Because Kw equals H plus times OH minus, you can use this to work out H plus and hence the pH. So let's look at an example. So like I said, to work out the pH of absolutely anything, you need H plus, and Kw is H plus times OH minus is concentration. And Kw equals H plus is concentration times OH minus is concentration. To work out the pH of a base, you need to find out what Kw is, which is generally given in the question, and OH minus is concentration, which you can work out using the chemical equation. Rearrange Kw to find H+, and then stick it into the pH equation. So let's look at an example together. Find the pH of 0.2 moles per decimeter cubed sodium hydroxide solution at 298 Kelvin, and they've told us Kw is 1 times 10 to the minus 14. Again, they include the temperatures not to throw you off, but because Kw and K, anything for that matter, varies with temperature. So like I said before with the steps, find out Kw and OH minus. They've told us Kw is 1 times 10 to the minus 14. And to find out OH minus, you can just write out the equation of the dissociation of NaOH. If you do that, you can see there's a 1-to-1 ratio between OH minus and NaOH, so the concentration of OH minus is the same as NaOH, so it is 0.2 moles per decimeter cubed. Next, we can rearrange Kw to find H+, so we know Kw equals the concentration of H+ times the concentration of OH minus. If you rearrange that, you get Kw divided, and if you stick the numbers in, you get a result of 5 times 10 to the minus 14. So now we have H plus's concentration, we can stick that into the pH equation, and that gives us a pH of 13.3. So whenever you're calculating the pH of a strong base, you need to use Kw. So let's try an example then. Find the solution of a 0.3 moles per decimeter cubed solution of potassium hydroxide at 323 Kelvin, and Kw in this temperature is 5.48 times 10 to the minus 14, because remember, it can change with temperature. So I'll let you guys try this question and then I'll show you the solution after. Okay, so remember, always find out what Kw and OH minus is. So they've given us Kw, it is 5.48 times 10 to the minus 14. We could work out OH minus by writing out the equation. You can see there's a 1-to-1 ratio between KOH and OH minus. So the concentration of KOH equals the concentration of OH minus, which gives you 0.3. We know that Kw equals H plus's concentration times OH minus's concentration, and rearranging that and putting the numbers in gives us a value of 1.83 times 10 to the minus 13 moles per decimeter cubed. Next, you work out the pH by sticking it into the equation and you should get an answer of 12.73. So we've talked about strong acids and bases, let's move on to weak acids and finding their pH and everything to do with them, and that's where Ka comes in, the acid dissociation constant. So calculations involving weak acids do not work with those previous equations. That is because their dissociation is only partial. Their equilibria is not as far to the right as strong acids. Since their dissociation is reversible and it lies a lot to the left, their equilibria actually plays a more important role. And this is where the acid dissociation constant Ka comes in. So let's take an acid HA. The dissociation of an acid HA is written as this, where it's an equilibrium reaction. You've got HA dissociating into H plus and A minus. Since this equilibrium is reversible, you can make an equilibrium constant. And if you remember, that is the concentration of all your products times each other over the concentration of the reactants. In this case, it would be the concentration of H plus times the concentration of A minus over the concentration of the acid. And that is what Ka is. It is an equilibrium constant just like every other one. And like every equilibrium constant in existence, it is only affected by temperature, which is why in questions they will include a temperature and the Ka value. It's not to throw you off. So let's take an example of ethanoic acid. Its dissociation can be written as this. So you got CH3COOH, the formula, dissociating into H plus and ethanoate ions. Therefore, this one's dissociation constant would be this. Ka equals H plus's concentration times the ethanoate ion concentration, all divided by the concentration of CH3COOH. And it's always important to work out the units as well. So if we look at the units of Ka, they are moles per decimeter cubed, because you are timesing a concentration measured in moles per decimeter cubed, because you're timesing a concentration measured in moles per decimeter cubed by another concentration with the same units, and dividing it by something in moles per decimeter cubed. So these moles per decimeter cubes cancel out, leaving behind moles per decimeter cubed as the unit. If we have a pure acid, we can assume that all the H plus comes from the acid. This assumption works because water hardly dissociates, so any H plus that increases comes from the acid. Therefore, H plus roughly equals A minus. So for a pure acid, you can make the assumption that Ka equals H plus's concentration squared over HA. This is used to work out the pH of a pure weak acid, as in nothing is dissolved in it. So we can use that assumption to find the pH of weak acids. If you have a pure weak acid, you can find its concentration using Ka. So for example, find the pH of a 0.5 moles per decimeter cube solution of ethanoic acid at 298 Kelvin, and they've told us that Ka is 1.75 times 10 to the minus 5. Again, the temperature is there because Ka changes with temperature. So you get CH3COOH goes to H plus and CH3COO minus. And if I write that in terms of HAs and A minuses, that's what it looks like. To find the pH of anything, we always need H plus, and this is a weak acid, so we can't use any concentration molar ratio stuff. You need to use Ka. If we use Ka, we've got H plus times A minus over HA, but because this is a pure acid, we can assume that H plus and A minus are roughly the same. So Ka equals H plus's concentration squared divided by the concentration of the acid. You can rearrange this to find H plus squared, which if we do that, gives us this, and we get an answer of 8.75 times 10 to the minus 6. We need to square root that to find the concentration of H plus, which gives us 2.95 times 10 to the minus 3, and then you slap it into the pH equation, and you get a pH of 2.53. And that is how you find the pH of a weak acid that is pure. So let's try an example where you're finding the pH of a pure weak acid. Find the pH of a 0.03 moles per decimeter cube solution of propanoic acid at 298 Kelvin, and Ka is 1.30 times 10 to the minus 5 moles per decimeter cubed. Just press play when you've done that and I'll show you the solution. So as always, write out the dissociation equation. So you've got CH3CH2COOH going to H plus and then CH3CH2COO minus. If you're feeling lazy, you can write that in terms of HAs as well and A minuses. To find the pH of absolutely anything, we need H plus. And because this is a weak acid, we need to use Ka. So Ka equals the H plus times the A minus over HA, all concentrations. And because this is a pure weak acid, we can assume that H plus and A minus are the same, giving us Ka equals H plus squared over HA. You rearrange it to find H plus squared and then you square root it, which gives you an answer of 3.9 times 10 to the minus 7. You square root that, which gives you an answer of 6.25 times 10 to the minus 4. And then you slap it into the pH equation, which gives you a pH of 3.20. So sometimes you might need to find the concentration of weak acids, you might have to work backwards. So let's take an example and work through it. Find the concentration of an ethanoic acid solution with pH 3.42 at a temperature of 298 kelvins, and Ka is 1.75 times 10 to the minus 5. So if you write out the dissociation equation, it looks like this. And again, if you're feeling lazy and you want to just do HAs, there's that. You can use the reverse of finding the pH to find H+. So if you remember from before, I said that the concentration of H+ is 10 to the minus pH, which should give you 3.8 times 10 to the minus 4 moles per decimeter cubed here. So now we have the H+'s concentration and we know what Ka is. We then use Ka to find HA, so we know that H+ and A- must be the same because it's a pure acid. So Ka equals H+ squared over HA. And we rearrange this equation to get HA, so you get this. And if you slap all the numbers in, you get HA to be 8.26 times 10 to the minus 3 moles per decimeter cubed, and that is the concentration of the weak acid. Sometimes they might ask you to find the Ka of weak acids, so let's take an example here. Find the acid dissociation constant of a 0.630 mole per decimeter cubed ethanoic acid solution with a pH of 3.42 at a temperature at 298 Kelvin. So write out the equation as always, or if you're feeling lazy, do an HAA minus thing. Write out the expression for Ka, and because this is a pure acid with nothing dissolved in it, we can assume that Ka equals H plus squared over HA, and then use the pH to find H plus, so we do the reverse, so it would be 10 to the minus 3.42, and that gives us an H plus concentration of 3.8 times 10 to the minus 4. So substitute the numbers you have into the expression of Ka you just made, which should give you this, and your answer should be 2.30 times 10 to the minus 7 moles per decimeter cubed. Let's move on to the logarithmic constant pKa. In a similar way to H plus ions and how they massively vary, Ka can also massively vary as well. So we can use pKa instead. So if we take pH is negative log to the base 10 of H plus, and to do the reverse and get H plus as concentration again, it's 10 to the minus pH. pKa uses the exact same thing, except instead of H plus as concentration, you're using Ka. So pKa equals negative log to the base 10 of Ka, and Ka equals 10 to the power of negative pKa. So let's do this example. Find the pH of a 0.060 mole per decimeter cubed methanoic acid solution at 298 Kelvin, and the pKa is 3.76. So let's write our equation out as always, and if you're feeling lazy, do an HAA minus. Just remember which one's HA and A minus. Convert pKa into Ka, so we do 10 to the minus pKa, which gives us 1.74 times 10 to the minus 4. Again, to find the pH of absolutely anything, we need H+, and this is a weak acid, so we need to use Ka. So write out your expression for Ka. Because this is a pure acid, you can assume that H+ and A- are the same, so you get Ka equals H+ squared over HA. Because we want to find H+, we need to rearrange this to get H+ squared from that equation, which gives us 1.04 times 10 to the minus 4. We want H+, so we need to square root that, and that gives us 0.0102 moles per decimeter cubed. Stick that into the pH equation and you get a pH of 1.99. Okay, so here are some examples for you to try. Calculate the pH of a 0.5 mole per decimeter cubed methanoic acid solution at 298 Kelvin, and they've told you Ka is 1.8 times 10 to the minus 4. Give that a try and then press play to see the solution. Okay, so as always, write out your equation of dissociation, or if you're feeling lazy, write HA and A minus. And again, to find the pH of anything, we need H+. This is a weak acid, so we need to use Ka. And this is a weak pure acid, so you can assume Ka equals H+ squared over HA. So you can see the pattern here. So you do all of that and you get 9 times 10 to the minus 5 for H+ squared, and then you square root that and it gives you 9.48 times 10 to the minus 3, and then you find the pH. So you stick it into the pH equation and you get 2.02. So okay, so try this example as well. Calculate the concentration of HCN that has a pH of 4.83 at 298 Kelvin, and Ka is 5 times 10 to the minus 10. As always, write out its equation of dissociation, or if you're feeling lazy, do the HAA minus stuff. This time we've been given a pH, so we need to use the reverse of finding the pH to find H+'s concentration, which if you do that is 10 to the minus pH, 10 to the minus 4.83, which gives you 1.48 times 10 to the minus 5 moles per decimeter cubed. You then use Ka to find HA, so remember this is a pure weak acid, so you can assume that Ka equals H+ squared over HA. You rearrange it for HA because that's the concentration of acid, and you get 0.438 moles per decimeter cubed. Here's another example for you to try. Calculate the acid dissociation constant of a 0.03 mole per decimeter cubed solution of propanoic acid with a pH of 3.30 at 298 Kelvin. So write out the equation of its dissociation, or HAA minus if you're feeling lazy. Use the pH to find H+'s concentration, so you do 10 to the minus 3.30, which gives you 5.01 times 10 to the minus 4. Substitute the numbers into your expression for Ka, so remember this is a pure weak acid, so Ka equals H+ squared over HA. See the pattern? And you get a Ka value of 8.37 times 10 to the minus 6 moles per decimeter cubed. And I swear, last example on pKa and Ka, calculate the concentration of a solution of ethanoic acid with a pH of 3.45 at 298 Kelvin. pKa is 4.78. So first convert pKa into Ka, so you do 10 to the minus pKa, which is 10 to the minus 4.78, which is 1.66 times 10 to the minus 5, and then you can use the reverse of finding the pH to find so H+ is 10 to the minus pH, which is 10 to the minus 3.45, giving you 3.55 times 10 to the minus 4 moles per decimeter cubed. Then you can use Ka to find HA. So again, because it's a pure weak acid, you can assume Ka equals H plus squared over HA. You rearrange it for HA, and you should get an answer of 7.59 times 10 to the minus 3 moles per decimeter cubed. Now I know you guys are probably sick to death of that, so let's move on to the chunkiest part, acidic and basic buffers. Buffers are solutions that resist small changes in pH when you add an acid or base, so they only work for small amounts. Acidic buffers are always made of a weak acid or weak base with a corresponding salt. And remember, one key thing to appreciate in anything to do with acidic and basic buffers is that the salt generally fully dissociates. And this entire topic is all about using equilibria. So let's take an acidic buffer. So again, like I said before, acidic and basic buffers are always made of a weak acid or a weak base and a salt that it makes. So it's made of a weak acid and one of its salts. So for example, propanoic acid is the weak acid and its salt is sodium propanoate. The weak acid, remember, always partially dissociates. So if we write the dissociation equation, you get that. Or if you're feeling lazy, you got your H plus, A minus stuff there. Like I said before, the salt fully dissociates. So you've got sodium propanoate dissolving into propanoate ions and Na minus, and you can see that is your A minus. This leaves behind an equilibrium solution of undissociated acid, HA, and its corresponding ion, A minus. So the HA in this example is here, and its A minus is here, and you can see you've got loads of A minus there as well. Adding an acid means adding H plus, and adding a base means adding OH minus, and that causes this equilibrium to shift and counteract the change, and that is an application of Le Chatelier's principle, which we'll discuss. Let's say we're adding an acid to the acidic buffer we've just made, so here's the equation of its dissociation, and here's it in HA and A minus. So remember, adding an acid means adding more H+. This causes the equilibrium to shift to the left to reduce the H+ ion concentration back to its original value. Because the H+ concentration changes back to its original value, the pH also does as well. In exams, always remember to say that the H+ combines with your A- and say what the A- actually is. So with this high budget animation, we're adding H+ here, and now there's too much H+. So the H+ combines with the CH3COO- to make more of the original acid and return the H+ back to its original value. And that changes the pH back to normal. Let's discuss what happens when we're adding a base instead. So we've got the same buffer from before, and we've got the same equation for HAA- and all of that stuff. Adding a base means you're adding more OH-. This time what happens is the OH- reacts with the H+, and that reduces the amount of H+ present. So you can see that's written here. This causes the equilibrium to shift to the right, and more of the acid dissociates to compensate and bring the H+ back to normal. And this changes the H+ concentration back to normal and hence the pH. Let's say we have two H pluses here, this OH- comes along and snags it, and this reduces the concentration of H+. The equilibrium then shifts to try and compensate and return the H+ back to normal, so we're back to having two in this example on that animation I've just showed. Okay, so let's move on to basic buffers. So these are made of a weak base and one of its salts, for example ammonia, the weak base, and ammonium chloride, its salt. Some of the ammonia reacts with water molecules and you get this. So you get the formation of ammonium ions and OH-. The salt always fully dissociates, remember, so you get NH4Cl dissociating into NH4+ and OH-. This leaves behind an equilibrium full of NH3, the weak base, and its corresponding ion NH4+. So adding an acid or base causes this equilibrium to shift and counteract the change. Let's use this example of ammonia then. So we've got our basic buffer setup here. Adding an acid means you're adding H+, so the H+ reacts with OH- and it gives you H2O. This reduces the amount of OH- present. So the equilibrium shifts to the right to counteract this change and return the amount of OH- back to normal. And since the OH- returns back to normal, the pH goes back to the original value as well. So let's say we have two OH- chilling at equilibrium. This H+ comes along and reacts with it and takes it away to form water. The equilibrium will shift to the right to return the OH- back to its equilibrium concentration and hence the pH. With this same equilibrium, let's talk about adding a base then. So if you add a base, you're adding more OH-. This increases the amount of OH- present. So the equilibrium shifts to the left to counteract this change as the OH- and NH4 react to give you NH3 and H2O. So it returns the OH- back to normal and hence the pH. So again, our very high budget animation here of adding more OH-, the equilibrium shifts to the left and the NH4 and OH- combine, and it reduces the OH- back to normal. What happens if we add water to buffers? So water does slightly dissociate into H+ and OH-, but when you're adding water, it shifts the equilibrium by the same amount in both directions. So the pH doesn't actually change. All it does is it dilutes the buffer. Now let's come to the most dreaded part of acids and bases, calculating the pH of a buffer. So the pH of a buffer can be calculated if we know the concentration of the weak acid and its salt. Remember that salts fully dissociate, so the concentration of the salt will equal the concentration of A minus. We can assume the weak acid is partially dissociated, therefore the concentration of the weak acid is equal to HA. Remember, the equilibrium is so far to the left, it's pretty much not dissociated at all. You write out an expression for Ka, and remember, whenever you want to work out the pH of anything, you need H+, and you slap it into the equation, and you're done. We'll do an example now. So let's take this example then. We've got a buffer solution is made of 0.5 moles per decimeter cubed ethanoic acid and 0.650 moles per decimeter cubed sodium ethanoate. Find the pH of this buffer at 298 Kelvin, and the Ka for this is 1.7 times 10 to the minus 4 moles per decimeter cubed. Now that's a lot of numbers, but if we break it down into the fundamentals, it shouldn't be too scary. So write out the equation for the dissociation of the acid, which is here, and here it is in terms of HA and A minuses. Write out the equation of the dissociation of the salt. Now remember, the salt fully dissociates. And to help picture this as well, I've written it in terms of A minus as well. You can see here that the A minus here corresponds to the A minus here. The salt fully dissociates into its A minus and A minus. Because the salt fully dissociates, the concentration of the salt equals A minus. So A minus in this example is 0.650 moles per decimeter cubed. We can assume the weak acid is only partially dissociated as well, so HA equals 0.5 moles per decimeter cubed. Because its equilibrium is so far to the left, it's barely dissociated. Because it wants us to find the pH, and this is a weak acid, we need to use Ka. So let's write out Ka and rearrange it for H+. Remember that because this is not a pure weak acid, there is stuff mixed in this now. You have to use the H plus A minus over HA. You cannot do Ka equals H plus squared over HA, that's wrong, because it's not a pure weak acid anymore. Rearranging all of that gives you this, which I'll let you just look at, and you get an H plus value of 1.31 times 10 to the minus 4, and then you slap it into the pH equation and it gives you a value of 3.88. So this is the technique you use when you have a solution of an acid already mixed with its salt. So the next style of question you might see is acids and bases making buffers. So when you add a small amount of strong base to a weak acid, you can actually set up a buffer like this as well. Because remember, a buffer of a weak acid is a mixture of weak acid and its salt. So if you mix a weak acid and a strong base, you're making a weak acid and salt. And this leads to an equilibrium mixture of H plus and A minus. To work out the pH of an acidic buffer where a base has been added, we need to do the following. So first you need to write out the equation of this reaction, which is a neutralization reaction, making a salt and water. You need to find the moles of acid at the start. You need to find the moles of acid and A minus at the end of the reaction, and then you need to work out the new concentrations of the acid and A minus, use Ka to find H+, and then slap it into the pH equation and you get the pH. So let's take an example here. A buffer solution is made by mixing 18 centimeters cubed of 0.1 moles per decimeter cubed sodium hydroxide with 35 centimeters cubed of 0.5 moles per decimeter cubed ethanoic acid. Calculate the pH of this buffer at 298 Kelvin, and the Ka here is 1.7 times 10 to the minus 4. So because they have a weak acid and they've mixed it with a strong base, we need to use this technique. So as always, write out the equation of this reaction that's going on. You've got your acid here, you've got your base, you've made your salt, and you've got water. That's the neutralization reaction. I'm going to do this in terms of HAs and A minuses to help it make sense. So your HA is here, the concentration here, and your A minus is here, and H plus, which isn't really relevant for now. We want to find out H plus. Start off by working out the moles at the start. So the moles of HA at the start is your concentration times the volume. They've told us the concentration is 0.6, and they've told us the volume is 35. So you would do 0.6 times 35 divided by 1,000. We assume that A minus at the start is 0 because this is a weak acid. So its equilibrium is very, very far to the left. Obviously, when you mix the two together, you're making A minus, so that changes. So now let's work out the moles of each thing at the end. Because you've added sodium hydroxide, it reacts with the ethanoic acid to make sodium ethanoate. But like I said before, the salt always fully dissociates. So the amount of A minus is going to be the same as the amount of the salt made, which is going to be the same as the amount of base added. We could work out the moles of A minus by working out the moles of the salt, which would all have come from the sodium hydroxide. So we could work out the moles of sodium hydroxide. That would be 18 divided by 1,000 times 0.1, which gives you 0.0018. Now that we've made 0.0018 moles of salt, the acid that makes up the salt must have come from here. So this actually drops by 0.0018. So the moles of acid at the end is the moles at the start take away the amount of A minus made. So now we're left with 0.0192 moles. Because everything to do with Ka revolves around concentrations, we need to work out the new concentrations. Because we've mixed two solutions together, the volume has changed, so we need to work out the new concentrations. Remember that concentration equals moles over volume, so we divide these moles by the new volume, which would be 53, because we're adding 18 and 35, and remember, divide that by 1,000, and that gives you a new concentration of 0.3622 and 0.034. We then use Ka to find H+, so remember this is not a pure weak acid, so you have to use H+ and A- all over HA. We know what A- is, we know what HA is, we've just worked them out. So now you can rearrange this to find H+, so you stick all the numbers in from what we got before, and you get 1.81 times 10 to the minus 3. You then slap that into the pH equation, and you get a pH of 2.74. And that is how you do this question every single time. Just follow this technique and you'll be fine. So let me give you an example applying that technique we've just done. A buffer solution is made by mixing 15 centimeters cubed of 0.1 moles per decimeter cubed potassium hydroxide, the base, with 27 centimeters cubed of 0.2 moles per decimeter cubed methanoic acid. Calculate the pH of this buffer at 298 Kelvin, and the Ka for this is 1.6 times 10 to the minus 4 moles per decimeter cubed. I'll let you try this, and then press play to see the solution. As always, write out the equation for this reaction. I've also included HAs and A- just to make this a bit easier. Work out the moles at the start by doing the concentration times the volume. So for HA, the moles at the start would be 27 divided by 1,000 times 0.2, and that gives you this. Remember, at the start, there is no A- because the reaction's not yet happened. The potassium hydroxide and the methanoic acid have not yet reacted. And also, the acid is so far to the left in its dissociation that there pretty much isn't any. You then work out the moles at the end. So now we work out how many moles of A- is made, which comes from the salt, which comes from however much potassium hydroxide was added. So you would do 15 divided by 1,000 times 0.1, which gives you 0.0015. The salt made has to have taken some of the acid from here, so this decreases by 0.0015. Because we mixed two volumes together, we've now got new concentrations, so we need to work out the new concentrations. All you do is divide these moles by the new volumes, so 15 plus 27 gives you 42, so your new volume would be 42 divided by 1,000, because we're working in decimeters cubed, and that gives you 0.0929 moles per decimeter cubed and 0.0357 moles per decimeter cubed. You then use Ka to find H+, and remember this is not a pure weak acid, so you can't do H+ squared over HA. You rearrange it to get H+ and stick all the numbers in, and you should get 4.16 times 10 to the minus 4. And then you slap it into the pH equation, and you should get a pH of 3.38. Here's a pretty interesting past exam question I found. If you want to try it, then give it a shot, but I'm going to walk through this together. The biochemist adds sodium ethanoate, which is CH3COONA, to 400 centimeters cubed of 0.2 moles per decimeter cubed ethanoic acid. Ka for ethanoic acid is 1.75 times 10 to the minus 5. Calculate the mass of sodium ethanoate that the biochemist needs to dissolve in the ethanoic acid to prepare this buffer solution. Assume that the volume of the solution remains constant on dissolving the sodium ethanoate. So this question wants us to work out the mass of salt, so we need to work out what A- actually is. Because remember, all the A- goes into the salt in these buffer questions. So what we do is we write out the equation as always, which is here, and I've put it in terms of HAs and A-. Work out the moles of everything at the start. So we could work out the moles of HA by multiplying its concentration of volume. So 400 divided by 1,000 times 0.2 gives you 0.08. And again, there's no A- at the start. Let's work out the moles at the end. And now this is where it gets tricky. They haven't told us how much sodium ethanoate they've added, so we can't really work out the moles here. However, we could work backwards. Looking at this question, we know Ka and we know the pH. So you can work out H+ by doing the inverse, so you do 10 to the minus pH. That gives us an H+ concentration of 1 times 10 to the minus 5. This question wants us to find A-. We can use Ka to do that. So if we write out our equation for Ka, we get H plus A- over HA. We can rearrange this to get A-, and if you stick all the numbers in, you get a concentration of A- to be 0.35 moles per decimeter cubed. The concentration of acid is here in the question, and because the volume's not changed when they've dissolved it, you can use that again. Ka has been told here, and the H+ we've just worked out. So remembering that the concentration of salt equals the concentration of A- because the salt always fully dissociates, you can work out the moles of A-. So the moles of salt would be the concentration times volume, and we just worked out the concentration of 0.35. We've been told the volume is constant at 400 centimeters cubed, and it hasn't changed when you dissolve the sodium ethanoate. So you do 400 divided by 1,000. That gives you 0.14 moles. We could then work out the mass of the salt needed by doing mass equals moles times MR. So if you look at your periodic table and you work out the mass of this, you times them together, you get 11.48 grams. Now, I know that's been a hefty video, but hopefully that clears up any confusion to do with acids, bases, and buffers. Thank you very much. And if you have any questions or spotted any mistakes or just any concerns, let me know in the comments. If you find this helpful, as always, please try to share this with other people. It helps and goes a long way. And thank you very much.